is Jason Resch. I'm from IBM, part of their cloud object storage team, which was formerly part of, is this better? Yeah, it's on. So I'm part of IBM's cloud object storage, formerly CleverSafe, and today I'm going to be talking about linearity, how erasure codes, encryption, and a number of other functions all have this property of linearity, which, as we'll see, enables them to be combined in some really interesting ways. So I'll begin by introducing and defining linear functions. I'll show how some toy examples of linear functions, and then the manners in which they can be combined. I'll then show and prove how erasure codes satisfy this property of linearity. And then that will be used as the basis for showing how erasure codes and encryption can be combined in some pretty surprising ways. Erasure codes and some integrity check functions can also be combined similarly. And then I'll conclude with showing some even more kind of novel applications of exploiting this property. So the math involved is probably a lot simpler than you think, but if there's anything that's not clear, feel free to stop me and I'll explain. So a function is linear if it satisfies the following relation. So we have this function f. If it so happens that f of x plus f of y equals f of x plus y, then we can say f is linear. In short, what we're saying is that if you apply some operations to the inputs of the function, and you get the same result as if you apply that same operations to the output of that function, then you have a linear function. So let's consider this function called mul5. All it does is take some input, it multiplies by, that input by 5 and returns the result as an output. Is this a linear function? So we can start by considering some example inputs. So let's say x is 3, y is 7. And we see mul5 of 3 is 15, mul5 of 7 is 35. And if we add 3 and 7 together, we get 10. Mul5 of 10 is 50, which equals the 15 plus 35. So, and this follows for any x and y. It's a consequence of the distributive property of multiplication. And that basically just says if you multiply 5 by x plus 5 within parentheses, it's the same as if you multiply 5 by x and add it to 5 times y. So we can conclude that mul5 is linear for the addition operation. Other functions are linear for other types of operations. So a lot of functions actually have this property. Among them is the cyclic redundancy check function, or CRC. CRC functions are commonly used in integrity checks for files, or it's used in TCP/IP as well. The way CRC is actually implemented as a function is it's what's called a polynomial division in a finite field. The details of what that means aren't really important, but you can think of it as basically an addition operation. But what's important is that within this finite field, addition is kind of defined a little bit differently from our common sense notion of addition. It's instead defined by the XOR operation. So given the definition of linearity, it follows that if you take the CRC of some message x and you XOR that CRC with the CRC of some other message y, the result you get from XORing those two CRCs together will be the same as if you calculate the CRC of the two messages x and y XOR together. In actual implementations, there's a small caveat, which is because CRC considers the length of the input, we also have to calculate the CRC of the string of all zeros having the same length as x and y in order for the math to come out. So here we see a short Python program that kind of demonstrates what I just showed. It first computes So it first computes this combined CRC of two strings, foo and bar. What this function does is first it generates a string of zeros. This will be 3 null characters effectively. Then computes the CRC of x, XORs it with the CRC of y, and XORs that with the CRC of the string of zeros and returns it. And then prints the result. And then right below that we see we create this combined string by XORing foo and bar together. And then we print the CRC of that. And before I reveal the result, does anyone have a guess about what the outputs will be? Sorry? Did anyone have an answer? All right, so even if you probably can't do the CRC in your head, you might have guessed that the result comes out to be the same. So we might say this is kind of an interesting curiosity, but how is it useful? Are there any actual practical applications of this? So before we can kind of see how it's useful, I first want to kind of give everyone a primer on encryption and how encryption works. So in their most basic form, you can view an encryption function as simply a random number generator, where the key acts as a seed to that random number generator to generate an arbitrarily long set of random output, which is called the key stream. This key stream is then XORed with the plain text to perform the encryption. So let's see what this looks like visually. So we start with a cipher. It gets initialized with a key that's equivalent to seeding the random number generator. And for each unique key, the cipher will output a different random sequence of bits. This is true both for stream ciphers as well as block ciphers operating in certain modes, such as counter mode or output feedback mode, for example. And then when you're actually performing the encryption, you, of course, have a message you want to encrypt. And the key stream and the message, well, the key stream will be generated to have an equal length to whatever is being encrypted. So the cipher can generate bits basically forever, but we only need as many bits as the length of the message. So we generate the random bits, and then we perform the XOR between the key stream and the message, which looks like this. So the XOR operation simply flips a bit of the plain text wherever there's a 1 in the key stream. So you can see there is a bit of the message that was 0. There's a 1 in the key stream, so we flip this 0 to a 1. Here there's a 1 in the message and a 1 in the key stream, so we flip this 1 to a 0. But where there are zeros, we don't do anything to the message. We only flip where there are 1s. So you might wonder, how does this provide any security? But it's actually fully secure in that you learn no information from the ciphertext about the message, because if you consider any one of these bits, you know it underwent a 50% probability of having been flipped or having not been flipped. So you can't guess the original bit of the message with better than a 50% probability, which is the same odds you would have had if you had not seen the bit of the ciphertext. And then decryption basically does the same exact process. So it generates, you put in the same key, you generate the same key stream, you flip all the same bits, and because you flip the same bits, you're back to the original message. So we know that the XOR operation that we used to implement an encryption is the same as addition in the finite field arithmetic used by CRC. So we can say that there's this relationship between the ciphertext and the plaintext. The ciphertext is effectively the plaintext added to the key stream. And therefore, because CRC has this property of linearity, we also know that the CRC of the ciphertext, so if we calculate the CRC of some encrypted data, the result will be the same as had we independently calculated the CRC of the plaintext and the CRC of the key stream and combine those results. So now we're kind of entering the realm where maybe we can find some useful spin or application of this. For example, let's say you had a backup client running on your computer locally, and it was not sending your files to your backup provider, but encrypted files. And the backup client wants to make sure that the provider has a legitimate copy of what was stored. So you might implement software that goes to the provider, asks them, hey, what's the CRC of this file I just sent you? The provider could compute the CRC of the encrypted file that was just uploaded, send it back to the client, and then the client can use this property to validate the CRC of the non-encrypted file it has locally without having to re-encrypt the file first. So if you were at the previous talk, you probably got a much deeper picture of erasure codes, but for those that missed it, I'll provide a kind of brief overview. Note, however, that I'm using T and N instead of K and N, but the numbers are the same. Yep. Yeah, so if you take this code example, this is an actual program that runs, and this is the output. And I didn't do any modifications to CRC. This is just the implementation that's in zlib. So I think it's the CRC-C.
Does the same property hold for MD5 or SHA?
No, cryptographic hash functions don't have the property of linearity, and they actually wouldn't be secure if they did, because you'd be able to modify a message and then know how that affected the output. So you could find collisions and other things like that. Yeah. Right, so an erasure code encodes T inputs into N outputs, and it can recover the original input from any T of those outputs. There are a lot of examples, including RAID 5, RAID 6, Reed-Solomon, Rabin's information dispersal, Shamir secret sharing. These all are effectively and mathematically the same operation. And they're all, as we'll see, linear functions. So to kind of provide a picture for this, imagine that we have some input data, maybe it's a file, goes into an erasure code, and N fragments are produced. Each of these could be stored to a different location, and then at some future time when you want to recover it, you don't necessarily need all 7 of these. You might only need 4 of them. So erasure codes are often used to achieve durability and availability. You split the file into a number of pieces, and it's reliable because you can survive N minus T faults in the system. And it's also efficient because the overhead is equal to the ratio of N over T. So like CRC and encryption, erasure codes also operate in a finite field. And encoding and decoding are implemented simply via addition and multiplication in this field. So we can say, and I'll demonstrate this on the next slide, that erasure codes are linear. They have this property that if you erasure code some input message X, you get a set of fragments. And if you XOR those fragments with the fragments you get from erasure coding another message Y, you'll get the same result as if you erasure coded the combination of those 2 messages. So here we see another program which demonstrates this property. So what we're doing is first we're initializing this code as a 5/8 code. So we're going to generate 8 fragments. Any 5 are needed for recovery. So the first set of fragments we encode over the string hello. So there are 5 characters input. We get 8 fragments, each 1 character in size as an output. And then again, we erasure code this other 5 character input and get another 8 fragments out. We then loop through all 8 of both the first set of fragments and the second set of fragments, XOR them together, and then print the result. And then in the second phase, this is where we XOR the inputs together. So we create a combined string of just XORing hello and world into a 5-character string. And then we print the erasure code results of the combined output. So when you run this program, you see the results are identical. You get the same set of 8 characters as a result of encoding. It doesn't matter if you XOR the fragments or if you XOR the source data that goes into the erasure code. You get the same result. So since encryption is addition, and because erasure codes are linear functions, we can say that this property holds. If we erasure code the ciphertext of some encrypted data, the result will be the same as if we erasure code the plain text and then XOR those results with the erasure coding of the key stream. So to kind of demonstrate all this, let's say these are the fragments we would get if we erasure code the plain text. So the plain text is yellow. Here we'll see the results if we erasure code the key stream. So the key stream is in blue. And remember, this is the relation that holds. The plain text XORed with the key stream equals the ciphertext. If we were to erasure code the ciphertext, so this is in green, we'll get this set of fragments. Then due to the property of erasure codes being linear, it follows that this relationship holds between all of the fragments of the plain text and the fragments of the key stream. So for example, if you look at the third fragment of the ciphertext, it will equal the third fragment of the plain text XORed with the third fragment of the key stream. This property can yield enormous practical benefits, especially in a distributed system where you're storing encrypted and erasure coded data. So for example, in a distributed erasure coded system, you could use this property to encrypt previously unencrypted fragments. So let's say a user uploaded a file, went through an erasure code, it got distributed to many different nodes. And then let's say at a future time, the user wishes that they had encrypted that file. So one approach is they can re-encrypt the file, they can put it through the erasure code and store it again and overwrite the original. But that's going to use a lot of bandwidth. You're going to have to basically re-upload everything. As an alternative, you could send the key to each of the storage nodes. The storage nodes could expand that key into the key stream, put it through an erasure code to find the fragments that correspond to the fragment that they hold, XOR them together, and the result will be a fragment that's identical to how the user encrypted their source data before they stored it the first time. You could also have data that was previously encrypted that you want to decrypt, and the storage nodes can do that for you. Or probably the most valuable application is you could rekey the data without any network transfer. So consider you have this very large distributed system where you have independent nodes, each holding a single fragment for every object that's stored. And let's say this storage system has 50 petabytes worth of encrypted data. And now, due to some policy requirements, you want to rekey that data. So if you were not aware of this property, you would have to use this approach where you download all the encrypted data, you decode it with the erasure code, you decrypt it with the old key, re-encrypt it with a new key, put it back through the erasure code, and then send it back over the network. So all told, you would have used up at least 100 petabytes worth of network traffic. But with knowledge of this property, we can skip having to send any of that data over the network. You simply send the old key and the new key to each node, and individual nodes can update the fragments that they hold without having to talk to any other node or the end user, and without having to decode or decrypt the original data. So to provide a kind of a picture for this, let's say what's currently stored on a given node is the erasure coding of the plain text XORed with key stream 1. So this is the old key, or key stream generated from the old key. And we would like to, and these are the properties that it has, but we ideally like to store is the erasure coding of, again, that same plain text, but now encrypted with a different key. As it happens, each storage node has all the information it needs on hand to do this conversion, if only it knows what the old and new key streams are. So if you provide every storage node with the old and new key, it can generate the key streams. It can then put these key streams through the erasure code and XOR it with existing fragments of encrypted data, which converts it to what we want to have stored. So if every storage node computes these two key streams and erasure codes them, or you can XOR them together and erasure code them, you'll get a result that when you XOR with what you currently store, effectively you're canceling out key stream 1 and substituting in key stream 2. So we've updated our erasure coded fragment. So now to kind of tie erasure codes back into some integrity check functions. So we know erasure codes are linear, and we also know cyclic redundancy checks are linear. How can we combine them in practical ways? Before I can really show how it works, we first have to dive a little bit into the math of erasure codes, but don't worry, I don't have any numbers. So erasure coding is effectively just a multiplication, but it's a multiplication by matrix. So you can say erasure coding is linear in the same way that that mul5 function that we looked at in the beginning is linear, because it's basically just a multiplication. So for a given T of n code, you have this n by t encoding matrix, which multiplies an array of your data and will give you a larger array of outputs as a result. So another way to kind of think of this and why it works is each row of this encoding matrix basically defines an equation, and we put the data in as variables into that equation, and we get a result. And then we're storing kind of the results of putting that data through n different equations. And then in the same way that if you have a system of equations with a certain number of unknowns, if you have enough results of those equations, you can solve for the unknowns. And that's basically how erasure codes perform recovery. So to make the following slides a little bit easier to follow, I've color-coded each row of the encoding matrix and matched it to the output value that's computed using the equation defined by that row. So for example, this fragment here in purple is a function of this row of the encoding matrix and the data. So basically, those are the only two things you need to compute any given one of these fragments is the row of the encoding matrix and the T inputs. When it comes time to decode, so at some future time, as you know, we only need any T of those outputs to survive to perform the decoding. So I think this is a 5 of 9 code. We have 5 surviving pieces. And I just put an X through any piece that we don't have, and I also put an X through any row of the encoding matrix that is irrelevant to the outputs that we have. And because kind of each row is kind of independent of each other, we can ignore them entirely. And the math still holds. If we took this 5 by 5 encoding matrix and multiplied by the data, we would get a vector containing the same output values that we have. So this leaves us with, let's call it a truncated version of the encoding matrix, which it will always be square when we have T surviving output values to decode with. So at this point in time, we have the outputs. We want to get to the inputs, but we don't know what they are yet. And figuring out what they are kind of requires solving this equation. So to do that, we multiply both sides of the equation by the inverse of the truncated matrix, which causes the truncated matrix to cancel out with from the whole left-hand side of the equation. So that leaves us with basically just the inputs, which is what we're looking for. So that's how kind of encoding and decoding work with erasure codes. So with this background, let's see what else this might allow us to do. We observed decoding as happening all at once. Once we had all T of the outputs, we do this one operation, we get back the data. But it doesn't have to be done like this. The decode operation can actually be broken down into at least T distinct steps, which can kind of each be performed independently, and you can combine the results later to get the data. So we had this vector of surviving outputs, but we can also view it as the sum of T, let's call them subvectors, each of which contains just one of the outputs and zeros in all the other positions. So for example, the node that stores this purple fragment can generate this subvector because he'll just substitute in zeros for the fragments he is unaware of. So to kind of decode one output value at a time, we can use each subvector, which contains just one of the outputs, to perform what we call partial decoding. A partial decoding of the input. So if we take just one of the outputs, multiply by the inverse of the truncated matrix, we get this result. It's not quite the data, it's kind of like a fraction of the data. And we can do this with each one of the outputs. So if we use a different output, and again, it'll be in a different position in this array, we'll get a different partially decoded result, and so on. And we can compute all T of the partially decoded results one at a time. So once we have all T of the partially decoded results, it turns out that when we add them together, the result is the same as had we decoded them all at once. This works because of the kind of distributive property of matrix multiplication. So when we do the decoding all at once, we're basically doing the same operation. It's just combined in such a way that you don't realize it's happening. But you can separate it out, do the operation individually on each piece. So basically, each of your storage nodes can compute this partially decoded result for itself. And when you XOR them together, you get the original data. So just as the ciphertext is the sum of the plain text in a key stream, we've seen how the original input can be viewed as the sum of T of these partially decoded results. So this means that the sum of the CRCs of the partially decoded results will be the same as the CRC of the data. So because this property holds where the sum of all these partially decoded results is the data, it follows, based on the fact that CRC is a linear function, that if we compute the CRC of each of these partially decoded results, and then we XOR all those kind of partial CRCs together, we'll get the CRC of the original data itself. So this finding is pretty significant. It means, let's say, maybe you have a database where you store some attributes about your data before you store it in some erasure coded storage. One of those attributes you might store would be the CRC of that data. And you can now use this property to validate the integrity of the fragments without having to send the fragments over the network. Basically, the client could go out to each storage node, tell it, give me the CRC of your partially decoded result for your fragment that you hold. And you do that to a threshold number of storage nodes. The storage nodes only send the CRC back to you, so that's just 4 bytes going over the network per fragment, and then the client XORs them together, and the result should match the CRC for the data that's already stored in the database. So linearity also has a number of very interesting applications for rebuilding, some of which will sound paradoxical, if not impossible. But I'm going to show you that it actually is possible. So for example, due to this property, you can perform rebuilding of lost fragments without having to decode the data first. So in the previous presentation, it was mentioned rebuilding is very expensive because you have to read a threshold amount of fragments over the network, decode them just to get that one lost fragment. But you can use kind of this linearity property where you take the partially decoded results, multiply that by the encoding, by the row of the encoding matrix for the lost piece, and you'll get what you could call partially rebuilt fragment. And if you add a threshold number of those fragments together, you get the missing fragment. So you can save significant bandwidth in some topologies. So for example, let's say you had 3 sites geographically distributed, and maybe you have 30 nodes total, so each site has 10 nodes. Instead of, and let's say you have a disk failure at one node, instead of having to send 20 disks worth of data over the network and over the WAN to perform that rebuild, you could have nodes at each site compute their partially rebuilt slices, XOR them together into something that's the size of one fragment. You do that at 2 sites, so each kind of sum of those partially decoded fragments contains the information of 10 nodes worth of data. So instead of sending 20 disks worth of data over the WAN, you're now only sending 2 disks worth of data over the WAN. And you can extend this with encryption in some neat ways, such that it's impossible to gain any information about the data even when it's being rebuilt. So you can now effectively have a secret sharing system where no node or no entity in the system ever learns the data or the fragment or share that's held by any other node. And you can basically maintain the state forever throughout drives failing and having to be rebuilt. No one actually sees the original data, but you're still able to rebuild. Yeah, and unfortunately, I don't have time to explore all of the math behind that, but I do have some references that link to another presentation of mine that goes into more detail on that method. So in conclusion, we've seen linear functions offer a lot of possibilities, and even just considering encryption and CRCs, those are just 2 functions. There are probably huge numbers of other unexplored areas. And what's nice about them is that they can all be kind of combined together. You can incorporate the CRCs, the encryption, and the erasure codes all together into an interesting system where you can validate the integrity of the data, you can rebuild the data, you can rekey the data without ever having to send that data over the network. Yeah, so encryption, decryption, and rekeying verify the integrity of erasure coded data without having to download it, and rebuild with minimal network transfer and without ever exposing the original data. So here's the link to kind of the slide presentation on secure and efficient rebuilding. Thank everyone. I thank you all for attending, and are there any questions?
Do you know, is there a way to recombine CRCs when the length isn't the same? You XORed by 0, but the work being blocked isn't the same. Can you repeat that?
Yeah, so the question was, is there a way to combine CRCs when the messages aren't the same? And I haven't actually experimented with that, but my guess would be that if you calculated 2 CRCs of 0 length, or 0 byte strings, or a string of all zeros for both lengths used, the math might work out, but I haven't tested it to confirm. Mhm.
The idea of not having homomorphic is because we don't want to leak cancellation, right?
Yeah, the reason CRCs aren't, yeah, okay, sorry. For the question was, this linearity property is often something we want to avoid for cryptographic functions like SHA-256, for example. And a famous example of how this bit people was in the original WEP standard, which actually used CRCs for validating integrity of encrypted data. And the reason it wasn't secure is that because of the linearity property, let's say you're an attacker and you want to corrupt some transmission in a way that the other person doesn't detect. Let's say you flip a bit in the message. Even though the CRC was encrypted, it was encrypted again with a stream cipher, which just XORs the result. So if you flip a bit, you would know how the CRC was changed, and you wouldn't even have to decrypt it to know how to update the encrypted CRC. You just XOR your modification to the CRC to the existing CRC, and then the person receives the packet, decrypts it, verifies the CRC, and isn't even aware of the fact that it's been tampered with. So for guarding against malicious corruption, I'd say CRC isn't something you'd want to use. But this is kind of assuming you have benign entities. So you're talking to storage nodes which you trust. And if that's over a secure connection like TLS, you might assume that so long as the node isn't colluding against you, then you could still trust the results of the communications.
And the follow-up question is, the same property applies to encryption as well, right? Because when I say encryption of a message with a key, and then I get the result, and if I encrypt the same message again with the same key, I'm not supposed to get the same answer. That's supposed to be non-deterministic. So though AES and algorithms give you modes which are deterministic, are we stuck with only deterministic modes?
Actually, so AES is fully deterministic, but you're always warned to never use the same key for more than one message, or if you do use the same key, use a different initialization vector. So AES is often, when you're, for example, in TLS, you use the same session key for encrypting different records, but each one is, you can initialize it with a different IV for each operation, and that's what kind of provides you protection against the attacker taking, because you're right, if you encrypt two different messages with the same key, you can XOR those ciphertexts together, and you'll get the first message XORed with the second message as the result, because basically the bits of the key stream cancel each other out, and you're left with the bits of the two plain text messages. All right.
Can you explain why you need to do the CRC with zeros as well as when you're doing very early on?
Yeah. So I don't have a great explanation for that, except that if this weren't true, then the CRC of any string of all zeros would always be 0. So that may be viewed as a weakness, like if, for example, a message got corrupted and a bunch of zeros were added to the end of the message at the beginning, then it may not change the results. So I think that internally, practical implementations of CRC factor in the length of the message in order to kind of break that property. So, yes, for example, if CRCs did follow this property exactly, then take any random message X. If you calculate the CRC of two of those messages and XOR them together, you'll always get 0 as the results, and if you XOR that same message with itself, you get a string of all zeros. So it would follow that any string of all zeros would always have a CRC of 0, which I'm guessing was undesirable, so they kind of tweaked it to avoid that. But you can note here that you can actually skip this step because XORing with a string of all zeros has no effect. So really, you can kind of ignore this whole part of the equation.
So
it's an interesting thought. I'm not sure that, so you could probably have an implementation of the erasure code that kind of generates the key stream as it's doing the erasure coding computation. And there may be some advantages as far as keeping the cache satisfied, because 0 is kind of operating on the same bytes as opposed to first do the encryption, then do the erasure coding. But I don't think it would actually save the number of ops performed, because you would still need to do that additional XOR to factor in the key stream into the input. Now, it's not to say, I do think it enables some kind of interesting applications where, let's say you have an entity that's doing the erasure coding, maybe it's CPU constrained. So instead of it doing the encryption, it tells the storage nodes to do the encryption. And kind of you can do this distributed operation. So you have all n of the storage nodes doing the encryption for you. So you can also do things like that where you have tasks performed on your data at different places now. All right, thanks everyone.